Howdy, and welcome to another ECEN 215 Principles of Electrical Engineering. The topic today is mesh current circuit analysis. So let's just go ahead and get started. So now we get to the point of this lecture today, which is mesh circuit current analysis. So let's talk about why we would do this method versus nodal methods. And technically, this also works both ways. There are sometimes reasons why you would use nodal voltage, and there are sometimes reasons why you would use mesh current. And it has to do with the number of total equations. So nodal voltage method, we have this equation here. We have, if we use this, we have a node here, I have a node here, I have a node here, and I have a reference node, right? So how many nodes is that? We got 1, 2, and 3. Now granted, a couple of these are pretty simple because node 1 and node 2 are kind of known. But technically, by doing this, and also I have to figure out currents 1, 2, and 3. So I have to write a set of equations for this. So we ended up with 3 equations using KCL involving I1, 2, and 3, which we can easily solve. However, if we use mesh current, which is what I'm about to describe, we only need to do 2 equations. And now, so using KVL, so Kirchhoff's voltage law, which is analogous to the current law, where current law is all about the currents entering a node. Well, the voltage law is dealing with a loop. We're dealing with the voltages around a loop. So if we use KVL, we look at the loop current I1 here, and we have loop current I2, and so we end up with 2 separate loops. We got loop 1, which is this, and then we got loop 2. Of course, there's an overlap between the two, and it's through R3, and we're going to go over that real soon. But by doing this, we now simplify the complexity of the equations, because we're only going to end up with 2 equations and not 3. So let's take a look at this particular problem right here. So we've got R1, R2, I3, and we end up with 2 separate loops. We got loop 1 and loop 2. And so let's write our equations for this. So we're going to end up with 2 equations. So let's start with equation 1. So number 1. And so what do we end up with here? So we're doing voltages. So remember, everything is going around following the arrow. So if you enter a negative terminal, it's a negative voltage. And if you enter a resistor, you have to do its positive based upon that direction of current. So let's take a look here. So we'll start with the VA. So we got minus VA. We'll follow the arrow. So the arrow is going this way, right? So we're going this way. And then we come to this R1. And the only current going through R1 is I1. So let's take a look at that. So we're going to go plus. Using Ohm's law, we end up with R1 times I1. And that's the voltage drop across here, right? Using Ohm's law. Ohm's law says voltage is equal to resistance times current. So we have that. Now we're going to go across V3 here, or R3, and we're going to get this voltage 3. So we could put in V3 here, and that all must equal to 0. But obviously this isn't V3. We don't want it in terms of V3. We want it in terms of R3 and I1 and I2. So what do we think this is? So I'm going to write it out real quick and then come back and modify. So what is voltage 3? Well, voltage 3, it's about the sum total, the net current flowing through R3. So what is the net current flowing through R3? So, well, we know, first of all, it is related to R3, so we can write that. And then we end up with I1, because that's the current that's leading, right? But there's an opposing current here, I2, so it's I1 minus I2. So that's where that comes from. So we can rewrite this entire set of equation here simply as R1 times I1, right, plus R3 I1 minus I2, and since the VA is negative, we just stick it over here, make it equal to VA. And that's it. That is equation number 1. So now let's go and do the same exact thing, but this time with equation number 2, with the second mesh. So this is number 1, and this will be number 2. So let's do the same thing. Following the arrow, I'll start with VB. I know VB, because we entered the positive side this time, right? We can go in this way. So VB plus, oh, we hit this mesh current, if you will. We've hit this net one. So R3. But this time it's a little different. Remember, it's all about, it's not V3, but this time we're going the opposite direction. So we're following the arrow here. We're following this arrowhead. So R3 is going to be I2 minus I1. The opposing current is now I1 now and not I2 because we're following I2. This is the mesh current for this. Then we have R2, the voltage across R2, which is going to be that, which is simply R2 times I2. And this all must be equal to 0. So rewriting both of these, just so we have a set of common equations here. So we have equation 1 is equal to R1 I1 plus R3 I1 minus I2 equal to VA. And equation 2 gives us, what do we get? We get R2 I2 plus R3 I2 minus I1 equal to minus VB. Now, in the end, we have 2 unknowns, and we have 2 equations. We can solve this algebraically, or we can solve this with the matrix method. So with this problem here, we're going to do the exact same thing. So we're going to write 2 equations. We got I1 and I2, and we simply want to write the equations. So let's do that. For mesh current number 1, this is equation 1. I've wrote 1 colon here. This isn't, the current I1. This is equation 1 dealing with loop 1. So let's write that. So first of all, we have this 100 volts coming in. So we have 100 volts. But I'm going to save that to the end because we know that goes to the other side since it's going to end up doing that. So we'll start with the 5 ohm resistor. So 5 ohms times I1. And then we're going to have this 10 ohm meshed version. So we have 10 ohms. And we have I1 minus I2, the net current flowing through it. So I1, so we're on this side, we're looking at this voltage, and we have current flowing through it, and then we have an opposing I2. So that's where this is coming from. And this is equal to 100 volts. That's it. We're done with node 1. Or not node 1, mesh current 1. So now we have equation number 2. So equation number 2, same thing. We're going to start with the 7 ohm, kind of work our way around. So we have 7 ohms. Now obviously you can kind of see what you can do here. I'm sure you're already thinking the same thing. 7 ohms plus 3 ohms, I2. I could have combined that and simply made it 10, which is true. Plus this drop here, which is going to be 10 ohms, I2 minus I1 equal to what? It's equal to 0. It's a total, the KVL says the loop around this must equal 0. Same here, must equal 0. It just so happens we had minus 100 and we just put it on the other side. So there's our 2 equations. And now we just need to solve for I1 and I2. So we have 2 equations and 2 unknowns. We can do this. And I'll leave you for the sake of exercise for doing this. So, all right, what about this one? So here we've got, again, two mesh networks. So we can do the exact same thing. Here, actually, we know something immediately off the bat. What is the value of I1? It's minus 5 amps. Okay, why? Because we're given that. This current is defined as going this way. In other words, I1 is that. Well, I1 has been defined, so we know I1 is equal to minus 5 amps. That is a known. Now, I could write an equation for the entire circuit. We know that the voltage drop across, the 10 ohms and the 5 amp, that this loop must equal 0. But the whole purpose of this is also to solve for I1. Well, we got I1, so we can kind of skip through that. So now we're going to focus on I2 here. So let's talk about that. Well, let's talk about that. We got equation number 2. So what do we got here? We've got 10 ohms going through this mesh. It's going from here to here because this is the flow of the current. This is this way that we're analyzing I2. So we have I2 minus I1, which is a known now, plus the current going through the 5 ohm resistor, the voltage drop across that, which is 5 ohms times I2, minus 100 volts is equal to 0, which we can rewrite as 10 ohms I2 minus, in this case, 5 amps plus 5 ohms times I2 is equal to 100 volts, right? So let's break this down a little bit further. We got 10 and 5, so we got 15 I2 minus 50 volts is equal to 100 volts. So I think at this point we can easily solve I2. So we got 15 I2 is equal to 15 ohms is equal to 150 volts, which then we end up with I2 is 150 volts over 15 ohms, which is equal to 10 amps. So here we're going to talk about super mesh. So we had earlier super nodes. Well, there's also super meshes. So here we have 3 meshes. We have our 3 loops. We have loop 1, loop 2, loop 3. Loop 1, the net current going through this stage here is 5 amps this way. That's not saying that I2 is 5 amps, and that's not saying that I1 is minus 5 amps. The net current, I1 minus I2, is 5 amps. So that's what that's saying. But to make it simple, we can combine this and create this thing called a super mesh. Because remember, KVL is the net voltage flowing through any closed loop must equal 0. So the emphasis is any closed loop. So what if we did a loop, say, around all of this? If we considered that closed loop must equal 0. So we're going to exactly do that. So what does that learn into? Well, we have I1, right, plus 2, so 1 ohm times I1, so this current right here, this voltage drop here, we're going to start here, so we have that drop, that's this piece. And then we have 2 I1 minus I3. Now, you've got to make sure that you take I3 into account, because I3 is running through the 2 ohm resistor this way, whereas I1 is running through it like this. So the net current through the 2 ohm resistor is this times the 2 ohms. Then we have this 4 ohms, this resistor here. Its net current is I2 minus I3, because I2 is going like this. However, I3 is flowing it like this, so you get the net current flowing through it, which is I2 minus I3. And then we're entering, since we're following this arrow, We're entering the positive terminal of the voltage supply, so we add it, and so we end up with this equation. All of that must equal 0. So this helps us reduce things. Now, what can we say about this? Well, we know that I1 minus I3, this is known, this is equal to 5 amps. And, or actually, take that back. I2 minus I1 is equal to 5 amps. We have that equation, and we can also write an equation for I3 as well. So in the end, we have 1, 2, 3 unknowns, which by definition means we need how many equations? We need 3 equations. So this helps us. This helped get us one main equation, but we also need others. So again, we obviously know equation number 2 is we can focus on this one here, which that one is simply starting with a 3 ohm resistor. You got 3 ohms times I3 plus, in this case, you have 4 ohms times I3 minus I2 plus 2 ohms I3 minus I1 equals 0. So right there you have equation number 2. And then again, as we talked about before, we have a third equation, a third relationship of I1, I2, and I3 relationship. We know that I1 or I2 minus I1 is equal to 5 amps. And we get that right here. So now we have 1 equation, 2 equation, 3 equation. So you have 3 equations and 3 unknowns, which means we can solve. So in summary today, we have seen the process for doing mesh current circuit analysis. Make sure you attend the Q&A session for some more details and information, and to answer all your questions that you may have. Thank you and have a wonderful day.